So we have a triangle with in-center I. All right, so let's draw the in circle, and I is the in center. Okay, N is the midpoint. So kind of similar to the last problem, a lot of the same points. All right, I'm going to close this. I think BC is a little bit slanted. N is the midpoint of arc BAC. And P is such that ABPC is a parallelogram. So basically we can reflect A over the midpoint of BC. And that's point P. Q is a reflection of A over N. Oh, really? Do you remember your solution? R is a projection of A onto QI. Okay. So yeah, let's see if you can figure it out again. So this N, this is R. We want to show AI is tangent to the circumcircle of PQR. It's kind of interesting. All right, let's hide some stuff, add a couple lines. So we have the perpendicular from A to QI. And then P is so that ABPC is a parallelogram. We want to show that AI is tangent to the circumcircle of PQR. All right, let me draw the midpoint of arc BC. Seems like it's going to be used. Oops. All right. Is there anything special about this point of tangency? Reflection of A across I is the tangency point. Okay. So what we could do is we could, reflect A across I. And then we want to show that QRFP is cyclic. A lot of reflections here. So I'll draw A, B, and P. So yeah, a homothety takes a homothety about A takes IDN to FPQ, right? Okay, so really suffices to show that NID is tangent to AI. And that's probably just an angle chase because we know A and I is IDB.
We need to prove also that that circle passes through the midpoint of AR. It is not just enough to prove that it is tangent.
Okay. Let's see. Does it pass through? Sorry. EI squared is ED. Wait, okay. Okay. So we could define F to be the midpoint, and then let's see, and then a homophily. So IN. I'm a little confused. So ND. Yeah, but we don't have the midpoint of AE. Is AQ tangent to that circle? It almost looks like it. Let's see. No, it's not tangent. So yeah, I'll draw it so it doesn't look tangent. Maybe something like that. We can show G lies on the circle NID. But I is not the midpoint of, like, hold on. So I'm a little confused about the homophily. So N is the midpoint of AQ, right? D is the midpoint of AP, but we don't have the midpoint of AE, right? See what I'm saying?
I is the midpoint of AF.
Oh, okay. Sorry. Oh, okay. I got a little confused there. I is the midpoint of AF. I thought F was the midpoint of IE. That's why I kept getting confused. All right. So yeah, G is not the midpoint of AR. So wait, do you want me to find G as the midpoint, or like it was in the figure? Okay, as the midpoint. So that should be G. Okay. And then you're saying NGI is 180 minus IDN. Yeah, it's the same theorem again, right? INA is IDB. Yeah. So we know that's cyclic.
We are done.
Okay, hold on just a moment. Let me hide this circle. So okay. So NID. Okay, so I'll say let AR meet the circle NID at G.
I think we should just define it as the midpoint. And then we'll use the similar triangles to get the angles.
Okay. So let G be the midpoint of AR. All right. And then we could try to show that that's cyclic. And that's because angle, yeah, how do we show that that's cyclic?
Khan wrote it in the chat.
Ah, okay. Oops. Sorry. Thought I copied it, but I didn't. That implies that NGID is cyclic. See how this comes out. Do a double backslash. See if that fixes things. Ah. Why does it do that? Let me just do this. Just do it as two separate things. Okay. All right. So we have NGID is cyclic. And then we want to show its tangent to AI. And that's by an angle chase, I'm assuming. Because angle DIE, we want to show that's angle, let's see, IGR equals ANI. Okay, so first we want to show that's tangent to AI, right? What's the best way to do that? So DIE is INE. Oh yeah, DIE is INE from the similarity. So EI squared equals EB squared equals ED times EN. That means that angle EID equals angle ENI. And that means that the circle NGID is tangent to AI. To AI. And then by a homothety at A with ratio 2, we don't even really need point F actually. We could just say by a homothety at A with ratio 2, Q R, oh, but we have to show this perpendicularity. Yeah. Oh, but we kind of already, yeah, where did we use the perpendicularity? So wait, NGI is 90 plus IGR, which is
You get
90.
90 plus something.
So wait, how do we know? So IGR equals ANI. Wait, how did we know that? IGR is ANI.
Because ARI is similar to AQI.
Because ARI is similar to AQI. Okay.
And we use that AR is the perpendicular because if that run true, we will get that NGR is 90 degrees.
Okay. Let me write that out.
Yeah, also it is used in similarity that the GEO King also said.
Yeah. Okay.
So now only just homotopy. You just do homotopy and then we are done.
Okay. So, all right. Then yeah, then we'll have to do it finish off. So ARI is similar to AQI. That implies that angle IGR equals angle ANI. There we go. And then by the homotopy, at by a homotopy at A with factor 2, PQR, the circle PQR is tangent to AI. All right, I'm going to move on to the next one. So yeah, once we used that, the ideas from the last problem, it wasn't too bad. Elmo 2020 P3. Let me first do some of the other problems first, just because first I want to do the ones that are synthetic GEO, and this one looked kind of interesting. So actually, you know what? Let's try that. So GEO King sent me a problem. GEO King, you mind if I share our chat? Or oh well, already. But basically it says if you have the 3 lines, okay, so if we have the 3 lines that form a triangle, and we can only use the perpendicular bisector tool in GeoGebra, can you construct the orthocenter of the triangle? So that's the problem. So I'm gonna write it up here. So Elmo 2020 P3. Oh, it must be a hard one then, right? Because it's a P3. So given the 3 lines forming the sides of a triangle, construct the orthocenter using only the perpendicular bisector tool. It seems surprising that that's that hard of a problem, but maybe it is really hard. I'm guessing you can also label points. Was this what the problem was? Janabel. Show that if the 3 lines forming a triangle are drawn, he can mark using this device, a pencil, and no other tools. Yeah. So yeah, we can work on this a little bit. I'm not sure if it's really hard though, but let's think about it. So if you reflect the orthocenter over the sides, it lies on the circumcircle.
we can't really do anything with circles in this problem.
Yeah. So one thing about the orthocenter is that it's if we could somehow get the parallel lines to if we could draw a parallel line to BC, then that would solve the problem. I'm sorry, a parallel line to BC through A. Because let's say, like, if we have these three lines, then the orthocenter of ABC is the circumcenter of this double triangle. And circumcenter we can just do using the perpendicular bisector tool. So,
but I think that we need to construct the orthocenter of this triangle.
yeah, so the orthocenter of this triangle is the circumcenter of that triangle. That's what I'm saying. Yeah.
And that's what, yeah, I get it now.
That's all right. So yeah, is there a way that we can get a line through A parallel to BC? Let's think about this. Yeah, we can mark the midpoint of any segment. So like we could mark the midpoints of A, B, and AC, and then oh really? How do we do the 9-point center?
Oh, well, we can just mark the midpoints of sides and then mark its center.
Oh, good point. So we could do the 9-point center that way, and we could do this.
We can also do circumcenter, so that is pretty close.
Yeah.
But I don't think we can just reflect some point using this tool.
Exactly. Yeah, so that's close, but yeah, we can't reflect it. That's the tricky thing. How do we draw midlines? We can draw the midpoints of A, B, and AC, but then how do we connect them? Okay. So I know we can't actually do circles, but I'm just going to do it just to try to get the circumcenter. The reflection of the 9-point center across the A midline. Okay. So actually, I don't even know if we can do like, because I don't think we have a straight edge, right? So can we actually find the midpoint of AO?
Yes, I think it just needs the points.
Okay, because like we could draw the perpendicular bisector of AO, but how do we get the midpoint? Yeah, we don't have a straight edge, I don't think. Okay. So yeah, those we can find, right? It's the circumcenter of ADF. Ah, that's a good point. Okay. So we could draw the circumcenter of ADF. That's the midpoint of AO. So that's G. We can also draw the 9-point center. So let me do that right now. So I'm going to erase the circle in just a second, but we have the 9-point center. And then how do we draw the line DF?
It is the perpendicular bisector of GM.
Ah, okay. That is, that's very creative. I like that. Okay, so yeah, we can draw all these lines. So we want the midpoint of ON. So O is the orthocenter of this triangle, N is the circumcenter. Oh no, we don't want the midpoint, we want the reflection of O over N. So yeah, if we could draw the parallel to GN through A, that would solve it. Or the parallel to OE. Basically, it's like we're trying to figure out how to reflect one point over another point. So O is the orthocenter of DEF. Let's draw the orthocenter just to see if it helps at all. Okay, I'm going to erase it. We could try drawing the, so G is the orthocenter of ADF. We could also draw the 9-point center of ADF. What if we drew like this? I wonder if there's some relationship between H. Yeah, if we can draw the antipode of A, that would solve it. But yeah, that would require like reflecting A over O. Like, I wonder if we drew like all the orthocenters and 9-point centers of these 4 triangles, if there would be any sort of relationship between that and the orthocenter of ABC. So yeah, let me draw on all those points. Whoops, sorry. Oh, I don't think so. We can draw a point G, but I don't know that we can draw the line AO. Yeah, I think you're right. Sorry. Okay, I'm gonna just draw these. So if I draw the centers of all these, 1. Oh, those are the midpoints of, yeah, AO, BO, and CO. And yeah, let me draw that actual orthocenter. See if there's any relationship. GH. Okay. Yeah, so we can draw this, this, and this. Let me change H to J. Yeah, it's so weird because yeah, H is all the way over there. So yeah, I can color it another color. Or how about green? A darker green, maybe. I'll do a lighter green. That looks okay. But yeah, it's weird. It's just all the way over there. I'm not sure how to get that. H is the circumcenter of the reflection triangle of O. Okay. We can draw GN, JN, and IN also. Oh, because those are the perpendicular bisectors of DF, DE. Okay. Yeah, so N is the orthocenter of GIJ. If we can somehow join AN, then we are done. So I'm kind of still wondering. AM passes the reflection of O across BC. So what if I draw the 9-point centers of ADF? Yeah, I don't know if that helps that much. I'm gonna erase those. Because yeah, H, we just need to get stuff. We can mark the midpoint of NO. Okay. It's almost like we're pushing the points inwards, but we need to push them outwards. I'm not sure what the best way to do that is. Yeah. I'm just trying to get a parallel through A to BC. I feel like if we can reflect any point across any point, that would almost be good enough. I wonder if there's some part of this where we choose like an arbitrary point. What if we take the perpendicular bisector of AE? Because sometimes with these problems, it's like you use projective geometry and you like pick an arbitrary point somehow, and then cross ratios make it work.
I doubt we can do something like that here. We don't even have a straight edge.
We don't have a straight edge, yeah.
How are we gonna project points?
Yeah, no, that's a good point. So GJFE almost looks like a parallelogram. Yeah, okay, I think we do have like GJFE is a parallelogram. IGDE and IJFD. We have a lot of different parallelograms here, a lot of parallel lines. Yeah, is H the orthocenter of another? Because I think we need to use points D, E, and F more, because we need, let's see. Like maybe we could like take the circumcenter of DJA, or we want to start getting some points out here so that then we can get back to point H, basically. No, you can't construct a circle. But for example, what's the circumcenter of ADE? That would be like over here. So yeah, you can't construct a circle, but it's not hard to get a circumcenter. Yeah, we want H to be the circumcenter of something. That would make either the circumcenter or the 9-point center of something. I don't know if there's some. So we know it's the circumcenter of like the doubled triangle. Is it the circumcenter of some other kind of triangle? Or 9-point center? Yeah, we need to draw more points like out here so that we could then like what if we took like the circles A, G, E, B, J, F, and C, I, D, like maybe H, and we took their centers. Maybe H is like, I'm really just guessing, but like I don't know if H is like the circumcenter of that or something. All right, you guys want to go back to the other problems? See if we can finish any of them, or do you want to keep working on this?
Maybe do this a little bit more.
Okay, sounds good. So what I'd like to do, here's what I'm going to try. What if I draw that triangle that I said, where we know that H is the circumcenter of this circle, but maybe it's maybe there's other points on that circle that we could construct. So we have this. Let me shrink the diagram just a little bit. So L MN. Let me draw that circle and let's see if there's some other points on this circle that we can construct. Whoops. So for example, like this point right here, I think that's going to be hard. Maybe this one. What if we, okay, C is the orthocenter of AH, B. Yeah, I want the circumcenter of some triangle to lie on this circle. What's this, the circumcenter of BOC? Well, yeah, I don't think that would be good. So yeah, if I draw A and E, no, I don't think the center of that lies on it. What about AGE? Don't think so. Maybe AGN. No. Let me check the chat. If we were able to find 2 points symmetric with respect to A on the perpendicular bisector BC, then we could draw the parallel through A to BC. How would we do that? Oh, you're like symmetric with respect to A. Or if we can join AN. So I could try a KE. AGO. I could try this. I don't think it works, but no. It's close though. What about AGE? That's out of the circle. AGK. Did I do AKE? That's not going to be on it. Or AOE. All right, I'm going to move on to another problem. It was a fun one though. It just looks really hard. Sorry. So we did this. That one looks kind of interesting. I might do that one. This one looks a little bit long. Oh, this is kind of interesting. So, yeah, so we end up drawing the mixed linear in circle. I usually like when I do, let's see. And T is going to be the midpoint. Well, no, we're going to draw them. Yeah, I'll just draw it the usual way. Okay. So this is how I like drawing mixed linear stuff. So you have this point, and then you see where it intersects these two. And you see where those intersect the sides. And then I think EHJ is the mixed linear in circle. Yeah. So this should be T. I'll call this M. And so we want to show the homophoty sending this to ABC. So Q is that point. We want to show it sends Q to the midpoint of IQ. So let's draw the midpoint of IQ. So it sends J to G, it sends H to F. We want to show, the circle HQ. Well, let's see. I'm going to hide some extra stuff. So it sends H to F, J to G. We want to show it sends Q. So let's draw the circumcircle of HQJ. And then wait. We want to show it takes that to the circumcircle of this. So basically we want to show those two circles are homothetic. So yeah, FG and HJ, we know those are parallel. We'd want to either show HQ is parallel to FD. Yeah, so if we could show HQ is parallel to FD, that would solve it. Maybe that might be an easier way to think about this. That's kind of interesting. So HQ is parallel to FD. Can we do an angle chase somehow? Yeah, how do we use that D as the midpoint of IQ? Okay, so we want to show HQ is parallel to FD. What do we know about this point D? Feature FD and GD. It almost looks like it meets it at the reflections of F and G over, or the perpendicular from G. I'm not sure if this is actually true, but let's see. Oops, sorry. Ah, that does look true. Okay, so somehow FD meets this. Oh no, it's not true. Mark the midpoint of FG. Okay. So yeah, that's going to lie on this line, because since I is the midpoint of HJ, then the midpoint of FG is going to lie on that. I is sent to E, that's true. Yeah, let me delete this circle. This is just confusing. So yeah, this whole THIJ is sent to TFEG, where F and G are the midpoints of these arcs. That's from my video on mixed linear incircles. And then we want to show that Q is sent to D. It's kind of weird, but Q is sent to D. Maybe we could use ratios. So we could try to show TQ over TD is TI over TM or something, or TI over TE. Or, because we want to show Q in this triangle corresponds to I in this triangle. So maybe we could show EI. We need to show FD squared equals FQ times FI in general. Are you sure that's right? FD squared is FQ times FI? Is there any way we can get the ratio QT over DT? or IQ over ED? We want to use that these are the midpoints of these arcs. Let's see. TBHI is cyclic. Good point. I forgot about that property. TBHI is cyclic. And we want to show, so maybe love signs to get TH is perpendicular to H. I don't think you mean, oh, TH over HF. We could, and then we'd have to connect that back to TQ and TB. Oh, TB squared is TQ times TI. Are you sure about that? Because D is the midpoint of IQ. So I wouldn't think that would, it's TQ over QI. Okay. And we have TQ. Yeah, point Q is hard to get a grip on. Is there another point on that like works well with the homophogy? So yeah, how do we use that midpoint, the fact? TH over HF. So you have TH over HF. That's sine TAC times sine ABT over sine B over 2 squared. Okay. And then, okay. And that's the same as TI. Okay, so you want TQ over QI. All right. And by ratio lemma in triangle TBI, TQ over QI. So BT over BI. Yeah, see if you can, that's a really interesting idea. We can compute BT over BI. How would we do that? Let's see. So we know BI, and then BT I guess T is kind of a well-known point, so it shouldn't be impossible to do that. Because that's sine BTI over sine BIT. And sine BIT, because we know G is the midpoint of arc. Yeah, okay, so a lot of trigonometry, I think, solves this problem. That's a good idea, Hakan. Let's see. Yeah, okay, so I'm gonna write out basically everything Hakan has said so far. So we have this. Let me get rid of the LaTeX, sorry. Okay. So we have that. And then we have this. And then, oh, whoops, it didn't copy right, sorry. Copy. Okay, and then we're going to try to get BT over BI. So we have BT over BI is equal to, that's going to be sine, sine BIT over sine BTI. And so BIT, so BTI is half of arc BAM, right? But BIT, it's half the sum of arc MG and arc BT. And I'm not sure how to get BT actually. I think there might be a way to get arc BT. So because there's actually, I'm not sure. So did you have an idea on how to compute BT over BI? Well, oh, I guess angle BIT is the same as angle BHT, which is half of arc AF. Yeah, but that kind of just gets us back in circles. All right, we are almost out of time. Oh, so it suffices to show, actually I can go 5 minutes more just because we started a little bit later. So it suffices to show that 2 times BT over BI is equal to sine, yeah, okay. And yes, so how do you calculate that BT over BI? Yeah, it might not be hard because yeah, T is like a well-known point. I'm just not sure at this moment. All right. So I'll write that out, what you just wrote. Whoops, sorry, it never copies correctly. So, do you think you have a way to calculate BT over BI? Let's see. TAC. I like that. Oh. BT over sine BAT equals AB over sine C. Okay, so you did that, and then BI. Okay. So let me delete this. I like this. I never liked trig in the beginning, but now I'm starting to like it a little bit. So let me, okay, let's copy this. I'm going to space it out a little bit. Yeah, I would LaTeX this up, but we're low on time. So, all right. And so, okay. And it looks like that should be enough information. So I know you're doing all the work. I'm just kind of looking at it and agreeing with it. So I appreciate everything you're doing here. Let me try to copy this. See if it works this time. Oh man. All right. Copy. Paste. There we go. All right. So I could say like, okay, so basically we have ABT and BAT. So yeah, the question is like, how do we know these two are equal? TA over TB or something. Okay, I think we're pretty close here. I'm gonna end the session just because we're out of time, but
just a moment.
okay.
Hakan said that we need TA over TB. That is something that we can compute because it is equal to AH over HB by the angle bisector theorem.
Ah, good point.
And those are the lengths that we can compute with some computation, but we can't compute them.
So yeah, TA over TB equals AH over HB by the angle bisector theorem. So we just have, yeah, there's got to be a way to do that because sine A over 2 is HI over AH, and sine B over 2 is, yeah. Let's see. So we'd have like, oh, but this H is not the foot of the altitude from C. Yeah, how would we get AH over HB? Because H is not the foot of the altitude.
If we introduce the all lengths of a triangle, then we could do it.
Like all the AH over HB is AI over BI. Okay.
I didn't say that, I think. Oh.
No, I'm writing what he put in the chat. So.
Oh, okay.
Is that right? So copy this. Okay. So combining. Okay, I'm just gonna write up like the combining the above, we get TD over BI equals TH over HF. So I'll say with some more work. We get TH over HF equals TD over, or TQ over QD. Which solves the problem. So yeah, thanks for looking through all this algebra. Yeah, so that should finish it off. All right, so I'm going to stop here. Thanks everyone for participating. You had a lot of really interesting solutions. And thanks everyone for watching on YouTube. So if you want to join us in future sessions, feel free to email me at mgreenb801@gmail.com. It's going to be in the description of my video. We meet every Sunday at 8 a.m. US Central Time. So thanks again and have a great day.